Good morning, I'm Mr. Precella, and this morning I'm going to work some anti-differentiation problems with my Math 1325 class. We're going to pick up where we left off during the last class. This is number 8 in y'all's homework, and first thing I would do is I'd rewrite that square root as t to the 9th plus 7t to what power? 1/2, same thing we've been doing all semester long, times 9t to the 8th plus 7 dt. And what do y'all think? Do we need a u-substitution? Yes, because we have a quantity raised to a power. If it's something other than just a variable to a power, my suggestion to you is to let u equal the thing that's being raised to the power. So u, I'd set t to the 9th plus 7t to u, and then du, what's du? 9t to the 8th, anything else? Plus 7 times dt, okay. Times dt. Oh wow, this was an easy one to start off with. It falls out very nicely at this point. Let's make the substitutions. That stuff there is going to become u, so we'll have a u to the 1/9. 9t to the 8th plus 7 dt is going to be replaced with du. So as I said, this one falls out very nicely. Rewriting it, we'll have a u to the 1/2. Wait a minute, I have an anti-differentiator. I'm just rewriting u to the 1/2 du. Now let's anti-differentiate u to the 1/2. That's going to become u to the, add 1, 1/2 plus 1 is 3/2, divide by 3/2, and we still have that plus c. And what's my trick for dealing with the compound fraction?
You have to take that 2, multiply the numerator and the denominator by the 2.
Okay, so I'll multiply the numerator and the denominator by that minor denominator of 2, so times 2 times 2. Oh, that pen's dead. I'll throw it away. So let's see, so that's what, a 2u, we have a, I'm running out of room, so I'm going to come over here, pushing this up some, that'll be a 2u to the 3/2 all over 3 plus c, and if we type that into my math lab, they'd give us an error, because there's no u in the original problem. What do we need to do? Okay, so let's get it back. U is equal to t to the 9th plus 7t. So our final answer would be 2 times t to the 9th plus 7t to the 3/2 all over 3 plus c. Any questions there? As I said, once we found the differential of u, we picked up the remaining factors in terms of t, so we didn't even have to modify. Usually we have to perform some sort of modification on this line right here, but not on this one. Any questions? Okay, here's another one. Number 9. Let's see there. Number 9. One thing I noticed, all those square roots, I think I'd rewrite the problem immediately as the integral of e to the z to the 1/2 all over z to the 1/2 dz. Remember I said, or I've recommended a u substitution anytime you have e to a power that's other than just e to a variable. If it's just e to a variable, then great, you probably won't need a u substitution. But if it's an e to some quantity, then yeah, you're going to need a u substitution, and try letting u equal whatever the exponent is on that e. So I'm going to let u equal z to the 1/2. And then du is equal to, let's differentiate, 1/2 z to the negative 1/2 something else dz. Okay. And you know something, it might be more obvious if the original problem here, we picked up that z to the 1/2. If we moved it up top, what would happen to that exponent? It'd become negative, so we'd pick up the z to the negative 1/2 at least, and we have the dz. So back over here, this is the original problem. Continuing on, we have pick that denominator up, move it up to the numerator to give us a z to the negative 1/2 e to the z to the 1/2 dz. And so we have a z to the negative 1/2 and a dz. Z to the negative 1/2 and a dz. The thing we don't have is this 1/2. So what can we do? Multiply both sides by 2 to give us a times 2 and times 2. So you have a 2 du is equal to a z to the negative 1/2 dz. And it's this line here and that line right there. Use those two lines to rewrite the integral, getting rid of the z variable. That's what we're going to use. So this stuff here, it's going to get messy now. That's going to become a u, and the z to the negative 1/2 dz is going to become a 2 du. Where do I put the 2? In front of the integral symbol, du. So let's see, we have a 2 times the integral of e to the u and a du. So what's the antiderivative of e to the u? Just e to the u. What do we do with the 2? Just bring it down. So we have the antiderivative of e to the u is e to the u plus c. One thing left to do. What is it? Okay, so rewrite that u as z to the 1/2 plus c. And I think that z to the 1/2 would look better if I wrote it as the square root of z, the way it was in the beginning. So 2 e to the square root of z plus c for my final answer. Any questions there? If you have an e to a power that's other than just a single letter, then my recommendation to you is to try u substitution and let u equal whatever the exponent is on e. We know that the antiderivative of e to a single letter is just e to that single letter. The derivative of e to the x is e to the x, so vice versa. Any questions? Okay. I find y'all are quieter when I'm recording, so it goes faster. So I don't have to worry. This recorder, the audio doesn't pick up what y'all say anyway. Y'all just sound like a mumble out there. Here's a word problem. This is ICALS number 10. The projected rate of increase in enrollment at a new college is estimated by d dt. The derivative of e with respect to t time is 7,000 times t plus 1 to the negative 3/2, where e of t is the projected enrollment in t years. So they're giving us the rate of change of enrollment. If enrollment is 2,000 now, when t is equal to 0, find the projected enrollment 48 years from now. Well, if we knew the enrollment function, all we'd have to do is just plug in 48 to determine what the projected enrollment is in 48 years time. Problem is we don't know the enrollment function. We know the derivative of the enrollment function. So to find the enrollment function, we're going to have to anti-differentiate that 7,000 times t plus 1 to the negative 3/2 dt. So to find e of t, the enrollment function, we'll have to differentiate the derivative, and once we do that, we're going to pick up that plus c, that constant of integration that we always have. We'll pick up a plus c, and that's a problem. So remember I said with these word problems, they have to give you something that you can use to determine the constant of integration. What did they give us that we'll be able to use to eventually determine that constant? The enrollment right now, it's starting off, they have to give you some sort of initial information. So when t is 0, the enrollment is 2,000. So we'll use that to find c. But we don't use it yet. We have to anti-differentiate that 7,000 times t plus 1 to the negative 3/2. What do you think? Do we need a u-substitution? Yes, because we have a quantity raised to a power. What should I try letting u equal? The thing being raised to the power, so t plus 1, let u equal t plus 1, and then du is equal to, the derivative of t plus 1 is 1 times dt, the differential of t, and I think that does it. Remember, constant factors take care of themselves. We don't have to worry about eliminating constant factors. Only variable factors, t plus 1 is going to become a u, and dt is going to become a du. So we have, let me separate off that. We use those two lines, and that's going to become a 7,000. We have u to the negative 3/2 du. So the constant factor of 7,000 we just bring down. U, add 1, negative 3/2 plus 1 gives me negative 1/2, divide by negative 1/2, and I still have that plus c. It's a compound fraction, so I'll multiply above and below by 2, the denominator. The minor denominator, I should say. Oh, this is working out real nicely. 2 times 7,000 is 14,000. What have we got left in the denominator? Negative 1. 14,000 divided by negative 1, that's a negative 14,000. Let's go ahead and replace that u with t plus 1, get it back in terms of the original variable, to the negative 1/2 plus c. There's my general enrollment function. The problem is that's plus c. That plus C could be plus 50 billion. It could be plus a negative 7,000 for all we know. So that's where we have to use these conditions they told us here. When t is 0, the enrollment is 2,000. So when t equals 0, E of t is equal to 2,000. I have to push this up now. I'm running out of room. So I'll set the enrollment function to 2,000. That's a 0 plus 1. 0 plus 1 is just 1 to the negative 1/2. 1 to any power is what? 1. So why do you have to resort to a calculator or rewriting using a positive exponent? I know 1 to any power is 1 times negative 14,000 is negative 14,000. So I really have 2,000 equals negative 14,000 plus C. So what's my constant of integration? 16,000. Add 14,000 to both sides to give me a constant of 16,000. So now I know that C there is actually a plus 16,000. So here's my enrollment function. E of t is equal to negative 14,000 times t plus 1 to the negative 1/2 plus 16,000. And let's see, they want to know, I'm going to have to slide it back down now. Let's see. They want us to now use this function to determine the projected enrollment 48 years from now. So 48 years from now, that means time is 48. So when t equals 48, what's the enrollment? Set t equal to 48, and you get the enrollment in 48 years will be negative 14,000 times 48 plus 1 is 49 to the negative 1/2 plus 16,000. 49 to the negative 1/2, that's if we move that down, that would be divided by 49 to the positive 1/2. 49 to the positive 1/2, that's the square root of 49, which is 7. Negative 14,000 divided by 7, I'm getting a negative 2,000 plus 16,000. I see Esteban punching on his calculator, so let's see if he agrees, if his calculator agrees with me. What are you getting? Let me scribble out that page 1. I'm getting negative 2,000 plus 16,000. I'm getting a projected enrollment of 14,000 students. Agree or disagree? Agree. So I agree with your TI calculator. So let's see. How low can I go? Anti-differentiated. Used a u-substitution. Unfortunately, I had that constant of integration. I had to use the initial conditions they gave us. When t is 0, the enrollment was 2,000. So the enrollment at the college, this new college, started off at 2,000 students. But 48 years from now, they're projecting an enrollment of 14,000. That's always risky over such a long time period, trying to project enrollment like that. Any questions? Okay. And one more. One more. This is like your number 11. Find the indefinite integral. Remember, an indefinite integral is the same thing as an antiderivative. What do y'all think? Do you think we need a u substitution here? Yes, because we have a function of x raised to a power. What do you think we should try letting u equal? Try letting u equal the thing being raised to the power. Try letting u equal ln x. Uh-oh, you're going to have to remember what the derivative of ln x is. What's the derivative of ln x? 1 over x dx. And I think we've got it. I think we've got it right here. Do y'all see it? We're going to come over. Let me rewrite. I'm a big writer, you know, so I like... Let me rewrite that. That's an ln x to the 11th all over x dx. So the ln x is becoming u. And then 1 over x, well, there's an assumed coefficient of 1 right here in the numerator. 1 over x dx. 1 over x dx is going to all be replaced with just du. I think it fell out very nicely. So all we have to do is anti-differentiate. We have a u to the 11th du. Any questions on those substitutions there? Now if we didn't have that 1 over x, if we didn't have that divided by x there, we'd have a problem. I'll tell you that much right now. We'd have trouble. But remember, u substitutions don't always work, but they are the most powerful tool you have for anti-differentiation. So, anti-differentiating, any questions on how I made the substitutions? Okay, so anti-differentiating u to the 11th, that's going to become u to the 12 divided by 12 plus my constant c. Now all I have to do is get it back in terms of the original variable x. So replace the u with the ln x. So we have an ln x to the 12th, all divided by 12 plus c. For my final answer. Remember, the derivative of ln x in terms of x is just 1 over x. Any questions there? Okay, well that should be enough to help you finish up your homework 12. No, homework 14, integration by substitution. So I'm going to take a little break. Bye-bye.